Hey everybody, this is your noon talk in track 4, technical changes since the last TOR talk. I'm Nick Mathewson. I'm one of the two main TOR developers. The other is Roger Dingledine, who's sitting there in the 4th row eating some pizza, and he'll be talking at 2. Two announcements before I start. The 1 o'clock sessions in track 5 and track, which one? And track 3 have been swapped so that Dan Kaminsky can have a bigger room. The second one is upgrade to TOR 01216. No, we're not kidding. Seriously, we're not kidding. Upgrade. We have reasons. All right, so let's go back to the future, or 2004, which was the last TOR talk at DEF CON. We had a pretty good TOR back then, and it was kind of a small network, but it was up and coming. A lot of cool hackers were using it. Pretty much only cool hackers and very, very determined people were able to use it because there was no GUI and you had to edit some files and read your logs and hope for the best and configure your applications. But, you know, we managed to get a couple of DEF CON talks out of the deal, and that was cool stuff. So what have we been up to since then? Mostly we've been hacking on TOR all the time. At least that's what I'm going to be talking about today. There's other neat stuff we've been up to, but this is the technical changes talk. We've been working on security. It turns out that our software wasn't perfect in 2004. Funny that. We've been working on scalability. It turns out that writing an anonymity network that can support a couple tens of thousands of users gives you the sort of software that will pretty much fall over as it gets to hundreds of thousands of users. And so as we've added more and more capacity, more users have shown up. Also, we've worked on usability, fixing usability bugs, adding GUIs. We've worked on performance too. That's not so much on the slides, but I'll talk more about it later. Integration. We've worked on trying to make it so that you can anonymize different applications with TOR that you couldn't before. And lots more. We have a changelog. We record stuff pretty religiously about what we've done. Check it out. Now we're up to... Our latest estimate is about 200,000 users, although it's kind of hard to tell since they're anonymous. But we've got about 1,000 servers these days. So I'm going to give you a brief, fast introduction to TOR on the theory that you've probably heard it before. Who here thinks they know how TOR works? Who here has used TOR at some point ever? Who here is still using TOR from time to time? Cool. Right. Once I've gone through TOR, I'm going to talk about directories and server discovery changes, which basically are making things faster and more secure. I'm going to talk about path generation changes, which will be more efficient and less filling, and I'll explain the fillingness later. I'll talk about ways that we screwed up some of our crypto issues subtly in the earlier revisions and how we fixed them, and some fun new tools and features that we've done. I'm really wired on caffeine right now, so if I speak too quickly, someone shout, slow down. So, intro to anonymity. Anonymity networks hide users among other users. So the idea is, if you're watching the network, you ought to be able to tell, all right, somebody's talking to Bob 1 and Bob 2, and Alice 1 and Alice 2 and Alice 3 are using the network, but I don't know whether Alice 1 is talking to Bob 1 or Bob 2 or what. So, that's anonymity networks. Here's TOR. There are a whole bunch of servers, where in this case a whole bunch is represented by 9, and they're all connected via TLS, which is also SSL. They're more or less the same thing. And there's a connection between every server and every other server. I just didn't draw it like that here. And these servers can come up and go down. Some are faster than others, some are slower than others. These are volunteer-operated servers running all over the network. You can run one yourself if you like. I'm not sure how well it would work if you tried to run one from your desktop in the audience, but give it a shot. Let me know what happens. So they're all connected via TLS pipes. Over the TLS pipes, they relay many circuits for clients. Each TLS pipe can hold many circuits. And when Alice 1, who's a client, in this case all of the clients are named Alice because they're anonymous, wants to use the network, she runs some software on her computer that builds her a circuit through the network. She extends it piece by piece. First, she connects to the first server. Second, she extends the connection anonymously from the first to the second, then anonymously from the second to the third. Pretty much all of our hops right now are 3-hop. I'm not going to explain why, but it's kind of an interesting argument. Right. After Alice has a connection to the last server in her chain, what does she do with it? Well, she probably wants to go somewhere on the net, like she wants to look at some pictures of kittens with captions under them, or whatever else people are using the internet for these days. To do this, she then sends a message that's encrypted with 3 layers of encryption to the first server, which takes off 1 layer and sends it to the second server, which takes off another layer and sends it to the third server, and then the third server gets it and says, connect to Bob, where Bob is an IP address and port. The stuff that is actually relayed and supported right now is TCP streams only, doesn't do arbitrary IP. Also, it relays TCP streams and not TCP packets. If you don't know the difference, you don't have to care about the difference. If you do know the difference, what I'm saying is that your favorite TCP fingerprinting attack doesn't work because we generate a separate TCP stream on the far end or exit node than Alice generates herself talking to the first one. This general design is called onion routing. Earlier designs for it are pipe. One earlier design that did the same thing was PipeNet. There are other implementations of the same basic design, but this is the one I know best because I work on it. So the general security properties you get are, if the first node, or someone watching Alice's connection to the first node is hostile, it can tell that Alice is talking. This isn't steganography. We don't hide the fact that Alice is using the network, but we do hide who Alice is talking to. Now, if the last hop... Oh, I've given it away now. Alice 1 is talking to Bob 2. If the last hop is hostile, it can tell someone has connected to Bob, but not who. However, 2 hostile hops can correlate the traffic patterns and tell that Alice is talking to Bob. That is, okay, these connections started at about the same time, they ended at about the same time, they had about the same amount of data, and the data followed the same pattern of bursts and pauses. There aren't any obvious fixes to this in the literature that don't involve slowing your network to a crawl. So when you start building an anonymity network these days, you basically need to decide, are we going to support web browsing and be vulnerable to this kind of attack? Or are we going to introduce multi-hour delays between Alice and Bob and resist these attacks but be useless for web browsing? We took the first approach because people seem to like this web thing. So first I'm going to talk about directories and server discovery. You'll recall before that Alice needed to build a circuit through 3 servers. Well, how does she find out that those servers are there? If you think about it for a while, you'll realize that every client needs to know pretty much every server in their path, because if you just go to one server, like in a lot of peer-to-peer networks, and ask it for a list of its neighbors, if it's bad, it could lie to you and tell you only other compromised servers. Also, all clients need to know the same servers. I'll talk about that a little more in a moment. Servers shouldn't be able to impersonate each other. If I can pretend to be the entire network, then I'm always the first and the last hop because I'm all of the hops. And the solution there is just what clients find out about servers is a set of self-signed descriptors. The way clients identify servers is by their public key. And assuming that, as Crypto Barbie says, factoring large numbers is hard, let's go shopping, you can totally rely on this to make sure that servers can't impersonate each other. Also, we don't want to use too much bandwidth to tell clients about servers. So why do clients need to know the same servers? I'll talk about this a little more in my next talk in an hour from now, but the basic reason is that if Alice 1 knows some servers, and Alice 2 knows other servers, and I can tell which servers they know, I can tell that some connections, like the one to Bob 1, could only have come from Alice 1, because only Alice 1 knows the server that's connecting to Bob 1. And there are ways you can make this attack even better, but that's the basic idea. So, back in 2004, when we last presented this stuff to you guys, we had a few directory authorities for a few equals 3. These were all trusted. Their IP addresses and their public keys were shipped with the source code, although you could override them, but we strongly suggest that you don't. And each authority would publish a big list of all of these self-signed server descriptors, and this would be signed with the authority's key. And the clients would go to an authority, download it, and go, oh, hey, yeah, that's right. And they'd use all those servers, and they'd do this every few hours or so. This was really slow, and it got even more slow as we added more servers. I think right now, so as soon as we're back from DEF CON, we're going to shut down this whole mechanism. If you're using TOR 010, TOR 010 will stop working. But that's really old, so no one's using it, we hope. But yeah, this was pretty slow. The files were really big, and right now they're up to like over a megabyte in size, and old clients are still fetching them too often. Yeah, this sucked. We added some caches, and this did help some. The clients wouldn't have to hit the authorities all the time, and anyone could run a cache, and because the documents were signed, there wasn't a security flaw there. But the files were still really big, and also, if even one authority was compromised, then they would generate presumably a compromised signed list, maybe containing only servers that were bad, and the cache would download it from them, and the client would download it from the cache, and the client would be screwed up. Also, most information in these great big directories was redundant. That is, you go at noon and you say, what's the directory? And you get a big signed list of 100 servers. You go back an hour or two later, you say, what's the directory? And you get a big signed list of servers of which maybe only one or two would have changed. So around 2005, we split the directories into status, which needed to be generated by the authorities, and individual descriptors. So you'd ask the cache, what do authorities A and B say? And you would get signed things from the authorities that would list the digests of every single router descriptor. Then you would go to the cache again and say, all right, I don't have the descriptor with digest such and such. Send it to me. And it sends it to you, and you make sure the signature is right and the digest is right. And you decide what to ask for based not on a single authority's opinion, but on the opinion of all of the authorities together. Now, why do we do this by digest of the descriptor and not by the digest of the descriptor's key? This was kind of a subtle point that we almost screwed up until we thought about it. There's a fun attack if you have a bad cache and a bad server working together, where I send one descriptor to the authorities with my ID, and then I send a different descriptor to every single client who asks for my descriptor from the caches. So in this case, the authority tells the server, use identity such and such, and the client says, all right, I'd like identity such and such to the cache, and the cache says, all right, here is a special descriptor for server 1 that only you will ever know about. And later on, when the client uses this special descriptor, which will have other information that only the client knows, the server will be able to tell the client from all other clients. The solution is to make sure that everyone has the same descriptor for every server that they use, and so this attack fails. So the remaining problems with this were that clients still had to go to the caches and ask for separate opinions from all of the authorities, and depending on when they asked, they would get a different set, and if they missed just one, they would compute a different value of what the consensus was for the different authorities. So what we're implementing right now, and I have it mostly done, but we still need to debug and test and actually deploy it, is a voting system where the authorities, now there are 5, but I couldn't fit all 5 on the slide, get together and vote on a multiply signed consensus status document. To do this, they get together every hour or so, and they all send each other's opinions. Once they've got all the ones that they're getting, they figure out, all right, what will the result of the vote be? They sign the result of the vote. It should be the same for all of them. Then, if it isn't, then they use whatever gets signed by the most authorities. Then they distribute signatures to each other, and until they have a single consensus with lots of signatures on it. And clients download these from the caches, check the signatures. If they can get one that's signed by more than half of the authorities they know, then they use it. And yeah. And at some point in here, I guess we collected all the underpants. So, also, there's more than just yes, no for each server in these statuses. There's lots of different flags that we set. There's named, which is, so, do we guarantee that this is the only server called such and such, or could there be other servers called such and such? Is it running right now? Is it valid? Valid is pretty nebulous. It basically means that we don't know any reason to totally distrust it, but we often don't find out about bad stuff. That's why we try to be resilient against some kinds of failures. Is it fast? Is it stable, or is it likely to go down pretty often? Is it a bad exit? Is it an exit at all? Will it relay traffic? Is it a current authority? And can you use it as a guard? I'll talk more about guards later. One of the neat things about our architecture now is that although actually determining these flags can be hard, the only thing that's really set in stone and sort of hard to change is how clients interpret these flags. So if fast means use this in a circuit that you will need high bandwidth on, then clients will have that behavior, and we can later on get more and more sophisticated at the authorities about detecting which servers are likely to be fast or not. And so clients will get better performance without having to upgrade. Although, once again, please do upgrade. Really. So other changes that we've made are in path generation. So you'll remember how Alice selected a path through the network herself, because if she asked someone else to do it, they might lead her astray. Well, one problem is in 2004, all of our servers were chosen with roughly equal probability, regardless of their capacity. So even if your bandwidth was X, and someone else's bandwidth was 2X, and someone else's bandwidth was 4X, you'd all get chosen for the same number of circuits. And that meant that big servers had lots of capacity that no one was asking for, and tiny servers were overloaded. I say the asterisk on equal is that we would also select based on your exit policy. That is your statement of, for the last hop, if you want a web page, we need somebody who will allow you to exit to port 80. We wanted to make sure that people could run TOR servers without relaying arbitrary traffic, so we built exit policies so that everyone can select which kind of traffic they'd like to relay. This means, though, that clients need to know these exit policies so they can find one that relays the traffic they want. But anyway, back to bandwidth. So the obvious solution was choose probability proportional to bandwidth, which was a pretty good idea. And of course, you need to select the believable bandwidth so that if someone says, hey, I can push really, really enormous amounts of traffic, no really, you don't give them 99% of the circuits. This is bad, first, because of trust bottlenecks. They would get all of the circuits. And second, because of resource bottlenecks. You could DOS the network by sending all of the traffic to a server that couldn't handle it. So, another problem is unstable servers. Say you've got some servers that go down every hour or so, and some servers that go down every 10 days or so. Well, a server that goes down every hour or so for a little while is still pretty useful for web connections, because most HTTP requests don't take an hour to fulfill. Whereas you don't want to use something like that for your IM or your SSH or any time when you want a really long-lived connection. So what we've done also is started tracking uptime, and when you have a server with really big uptime, we label it as stable, and we remember which ports need stable connections. That's configurable if you know of one that we don't. So when a client wants to connect to port 22, which is SSH, it will select a path consisting only of stable servers. Whereas when it wants a web page, it won't restrict itself to stable servers. So originally we selected paths at random. This bit is a little tricky. I'll try to go a little slow here. We would select, and the problem with this is profiling. So what you're trying to avoid in a network like this isn't necessarily just some of your connections get broken. Sometimes it's bad if any of your connections get broken. For instance, if you visit, say, cuteoverload.com every morning in order to see pictures of adorable kittens and hamsters, and you don't want anyone to know this because you're trying to, be really tough. You're in the Hells Angels or something. Then what you're trying to avoid is not, sometimes it is not any particular eavesdropping and discovering that you go to Qt Overload. You're trying to avoid anyone ever knowing that you go there. So if even once your stream to there is compromised, you lose. So what this means is that if you keep picking a new first and last node every morning, eventually you will get unlucky, and eventually you will choose a first node that's trying to get you, and a bad node that's trying to get you, and everyone down at the biker bar will find out, we'll call you Hamster Guy, and that's no good. So the trick here is to choose some fixed first hops. That is, choose a few that are your favorite. If they are compromised, you lose. However, if they aren't, then you're actually in decent shape now, because now you will not eventually choose a bad first hop. This idea isn't original to us. It was originally called helper nodes. We did some user surveys and figured out that nobody could tell what helper meant in this case, so we chose guard instead. And if your guards are good, then you are fine permanently. However, if your guards are bad, you're still fine. But at least now you've got a chance that your love of hamsters will be kept secret. So, what if the guard nodes go down? I said they were held fixed, but we actually needed a way to handle it if one of them goes down. Well, you got to pick some more. But the trick is that you don't want to eventually go through the whole network. So you've got to make sure that when they come up again, you go back to your original set of guard nodes. So you keep them in order, and you use the first 3 for certain values of 3 that happen to be up at any given moment. So you may have a list of 10. If the first one is up, and the second is down, and the third is down, and the fourth is up, use the first and the fourth. And it's even more complicated than this, and Mike Perry might talk about this at his talk, or he might have already enough stuff to talk about. So another problem is that old TOR built circuits on demand. You would say, I want to connect to IM. And then it would go to the first hop and do some public key. Then it would extend to the second hop and do some public key. Then it would extend to the third hop, fail, because the third hop wasn't there anymore, go oh crap, and start all over. And meanwhile, you are waiting for your website to load. So instead, we predict which ports you're going to want and preemptively build circuits there. So if you've been asking for port 80, port 22, and port 8001, we try to make, and you seem to be online recently, we try to make sure that you've got live circuits ready for use to those ports. Also, in case you ask for something that we can't do, we cannibalize an existing circuit and try to extend it only one hop and see if that works. That way, it's still a little slow, but it's faster than if we had built the circuit from scratch. All right, how am I doing? Wow, I'm doing really well for time. Must be the caffeine. All right. So previously we would extend by IP and port. That is, when you were connected to server 1 and you wanted to connect to server 2 or extend to server 2, you would say connect to server 2 at this IP and this port. And once you were there, you would do some handshaking that made pretty sure that you were talking to server 2 via public key. But on the way there, server 1 needed to build a TLS connection to server 2. So if server 1 didn't know the key for server 2, it wouldn't know which certificate to expect from server 2 when it did the TLS SSL handshake. Originally we thought that this wouldn't be a problem because all of the servers would download all the directory often and know all the other servers. In practice, this didn't work. One server would show up in the directory and a client would find out about it before all the other servers did, and it was a bad scene. The solution here is to use identity key as well as IP. But you don't want to, so that you say extend to server 2 with this IP, this port, and this identity key. But you don't want to identify only by identity key, because there's a fun man-in-the-middle attack here, where a bad Alice tells server 1 that you go connect to server 2 at this evil IP and this port. S1 goes there. The evil server relays the connection. And now the evil server, because of TLS, it can't actually read the contents of the traffic between S1 and S2. But now S1 thinks that its TLS connection to S2 travels through the evil server. And so the evil server can look at all of the traffic patterns and all of the timing and all of the volume between S1 and S2 and try to use this for traffic analysis attacks. This was no good. So you need to use the identity key and the IP and the port to do this. And this took a bit of thinking, but turns out it worked. All right, now we're getting a little crypto heavy. How many people here know what Diffie-Hellman is and how it works? How many people don't know but would like to understand the next couple of slides? Okay, cool. Diffie-Hellman is a way that two parties can come up with, assuming that they know that they're talking to each other, can come up with a secret key that no one else knows, that besides them, without ever sending the key over the wire. Basically, we use some generator G, like 2 to the 16th plus 1. We use a big prime. It doesn't matter if everyone knows what the big prime is. I send you G to the power of X. You send me G to the power of Y, both modulo that large prime. we keep x and y secret. So I now have g to the y and x. You now have g to the x and y. Well, we can now both calculate g to the xy, but nobody else can based on the information we have exchanged. So that's what all of this g to the xy stuff is about. And it'll come up in a minute. But one of the problems with our earlier protocol was it was kind of needlessly slow in that Alice and the first server in her path had already done all of this handshaking in order to establish their first connection via TLS. And then they immediately did exactly the same handshake again to establish confidentiality, which they already had from TLS, to establish integrity, which they already had from TLS, and to make sure that they were really talking to each other, which TLS already guaranteed. So we managed to cut out the initial first hop crypto in half just by making a fast path for creating your first hop inside TLS. And that helped server CPU a little bit. Server CPU is way more important than client CPU because each server has to handle tons and tons of clients. And speaking of cryptography, there was a problem with our crypto. We sort of hoped that either we hadn't thought about this or we thought that OpenSSL would take care of it, but there are some really bad values for x and y when you do Diffie-Hellman. For instance, if I pick 0, well, anything to the 0 is 1. So later on when you send me g to the y and I raise that to the 0, I'll get 1. And the problem occurred when Alice was extending through a bad server to a good server. She would send something encrypted with server 2's public key saying g to the x. The bad server knows server 2's public key, so the bad server can replace it with g to the 0 encrypted with server 2's key. Server 2 will send back, okay, you picked 1, okay, 1 to the y is 1, and it will send back g to the y, and the bad server could then replace g to the y with g to the 0 again, and now the client and the server think they have a secret key that no one else knows, and their secret key is 1. And while yes, 1 is as good a random number as any other number, when it's forced, that's bad. So this was pointed out to us by hey Roger, was this one that an anonymous person told us about? Yeah, we got an anonymous tip on this one. We still don't know who found this. If you ever want to fess up, that would be really cool because we think you're cool. But anyway, once we fixed this, Ian Goldberg, who's a prof at University of Waterloo in Canada, managed to prove that this aspect of our protocol at least was secure. Also, we sent in a patch to OpenSSL for this. So if you're using a recent version of OpenSSL to build your crypto protocol and you just went, oh crap, don't worry, OpenSSL will now catch this for you. So, new tools and features. So in the old version of TOR, everyone had to speak SOCKS. SOCKS was all that we understood. And the way SOCKS works is you want to do an anonymous TCP connection to a certain IP and a certain port. So you connect to your local SOCKS proxy and you say, connect me to this IP and this port. And it goes off and it does it. In TOR's case, it builds all of the circuits. In a normal SOCKS case, it just grabs a TCP stream. It just opens a TCP stream to wherever you're going usually. Well, the problem with this is in some cases it's easy. If you have, maybe your browser speaks SOCKS already, maybe your browser goes to a proxy that does some useful stuff for you, like Provoxy, which filters out certain kinds of headers, or Polypo, which is pretty fast and can filter out certain kinds of headers, and that converts it to SOCKS. Maybe you're using an application like Game, which I guess is now called Pigeon or something. It's an IM client, it's pretty good. It speaks SOCKS already. But say you've got some monstrous application that does a bad job of SOCKS. What could you do? Well, we had some solutions. They all kind of sucked, but, you can use something like tsocks or dsocks to replace all of the libc calls to connect and so on with calls to SOCKSified equivalents. This works on most free Unixes. This doesn't work on OS X. If you know how to shim libc calls in OS X, please tell me, because we searched pretty hard and didn't find a good way. DSOX can sort of do it, but not too well. And Windows was pretty screwed. Here, Windows is still you could do a net driver that converted everything to SOX, but that kind of sucked. You could another solution was, well, actually no, that wasn't a good solution. Never mind. All right. So something that we've added recently, though, that's turned out to be pretty useful, especially for integrators, is IP tables on Linux and PF on BSD and OS X support transparent proxying, which means that you can tell your firewall rules redirect every TCP stream to this local port, which any good firewall can do already. But what they add is that feature where the application can then say, hey kernel, hey network stack, I just got this connection. Where did the application want it to go? And once you know that, you as TOR can now build a connection to the right place, and the application never needed to speak SOX in the first place. Another neat solution that's getting popular and is being used by tools like GenesVM is to actually have a VM being your router. So you set your router to a local virtual machine, which is using tricks like this to convert all of your traffic to TOR. And because this machine is your router, you don't need to worry about applications accidentally sending traffic somewhere else besides your router. So another problem that we had, and have had for a really long time, is DNS leaks. Say you have an application that is written like most applications. You asked to connect to naughty.com. I have no idea what's at naughty.com. I probably should have looked it up first to see what I've just linked to in my slide. Oh well. So your application will do a DNS lookup and say, where is naughty.com? Your DNS server will say the address of naughty.com, 1234. This is not the actual address of naughty.com. And then your dumb application will go to TOR and say, over SOX and say, get me 1234. Now you can see the problem here. Your DNS, you just broadcast to your DNS server, hey, I'm looking for naughty.com. And then you use TOR to go anonymously somewhere. No one can tell, except your DNS server. And if your DNS server did a recursive lookup, well, yeah, a lot more people now know. So one solution that we had to recommend for a while is there are variants of SOX that instead of an IP address take a host name. SOX 4A always takes a host name. SOX 5 optionally took a host name. So we had to find applications that either supported SOX 4A or that claimed to support SOX 5 and could actually do it right. This is kind of hard to find and hard to explain and hard to convince application writers that they actually want to do it, because the whole first lookup, then connect path is pretty firmly hard-coded in a lot of applications, and our user base still isn't quite big enough to force the IE team to do whatever we say. So new solution is that TOR, as of 0202 alpha, now can act as a DNS server. So you set TOR as your DNS server, either by saying, hey TOR, listen on port 53, or hey TOR, listen on port such and such, hey firewall, forward 53 to such and such. And then you set up localhost TOR as your DNS resolver. And now when you ask TOR, it just does the lookup for you anonymously, sends you back the answer, and when you connect there, you're fine. Another neat feature about this is that so there are some special addresses that TOR knows how to handle, like addresses that end with .onion are for hidden services, which I won't talk about here. Addresses that end in .exit force TOR to use a exit node that you have selected. So previously, if you sent one of these to your DNS server would have no idea what to do with it. Now TOR can remember, oh hey, you asked for naughty.com such and such .exit. I'm going to send you back an IP that isn't the IP of naughty.com. It's an IP that I will remember, so that later on, when you ask TOR for that IP, it says, okay, this means go to naughty.com using such and such as an exit. And we choose IPs for this from 127 dot and then the high parts of net 127, so that if you screw up and actually try to connect to one of these, the connection won't leave localhost. Another problem we've had is that editing text files All right, it's not hard for people in this room, most likely, but remember that anonymity networks hide users among users. So, if a system that's only usable by the people in this room is not nearly so good as a system that's used by nearly everyone, it's because it's more useful to hide among 200,000 users than it is to hide among a couple hundred users. So what we did is we made an interface that, a so-called control interface that listens on a local port, and different applications can connect to it and be your GUI. And it also lets you, and they can do configuration, they can help you set up a server, they can help you see where all of your paths are going, they can put up pretty maps of the world with all of the servers listed on them, and you can watch traffic bounce around like in Sneakers. Apparently, watching the traffic bounce around like in Sneakers was a really big user request. Other neat things you can do with these are you can trap different requests to Tor. Like you can you can set up something if you think you've got a great new idea for how to build circuits or a new circuit building algorithm that you want to hack around with and test to see whether it's really faster than the one Tor is using. You can override Tor's default behavior for all of this stuff. Yeah, and now, gosh, I went through that really fast. Okay, now I have time for a whole lot of Q&A. Let's see. First, just some things you can do later on. Tor is at https://torproject.org or tor.eff.org. Try it out. If you want to run a server, run a server. We have documents and specifications that are pretty darn thorough and can tell you any more information that I left out here. You can donate to Tor. We are now a U.S. nonprofit charity, 501c3. You can write us off on your taxes. You can donate to the EFF as well. Due to Cindy from EFF doing me a favor last year, I'm doing the dunk tank for them at 6:30. If anyone has ever used Tor to do anything you didn't like, or if Tor has ever broken in a way that you didn't like, and you're mad at the developers for some reason, you can drop one of them into water for a modest fee. I'm talking at 1, which is right after this, on social engineering attacks against anonymity networks. Roger is talking at 2 about new anti-censorship features that we're doing, and Mike Perry is talking at 5, is it, Mike? 5, about securing the network and securing applications and stuff. And yeah, if you have a question, shout it out. If you wanted to do the Q&A after the talk, I have another talk right after this one, so I will be in the Q&A room for this track at 3, at 2, not at 1. So who's got a question? Yeah. Ooh, between now and the next DEF CON? Okay, the question is, what kind of technical changes do I expect between now and the next DEF CON? That's a pretty good question. Let me grab my laptop and look at our to-do list, which you can look at too on the web in our SVN repository. We don't yet have enough people to do a really, polished roadmap like real projects have, but we've got some pretty neat stuff lined up. I can't hear you. Okay. So, on the to-do list, we're going to get directory voting done. That's a big thing. We're going to get anti-censorship features in. We're going to try to be better about letting you decide as a Tor server how much bandwidth you want to give to other people and how much bandwidth you want to give for yourself. We're hoping to get done features that will create incentives for people to run servers by giving people who run servers better performance. This has some anonymity issues because obviously you don't want it to be totally obvious that you are running a server because you get a fast connection. So that's a little tricky. What else are we up to? Fixing lots of bugs, trying to get more secure. Let's see, voting's a big one. Refactoring. For a long time, we've wanted to switch our transport to UDP instead of TCP. I don't think we're going to have time in the next year. Hey, Roger, what else? Yeah, blocking resistance is really the big one. Roger's going to be talking about that at 2. We kind of hope that at this time next year, this Tor is censorship resistant by design and not just by accident. I'll probably think of other stuff too and like shout it out as stuff goes along. But yeah, you had a question?
Yeah, it seems like I saw a talk years ago where you guys have funding from the government.
Yes, all of our funders. Do you want a list of funders, or do you have a question about the Navy in particular?
Well, you still receive government funding.
We are receiving funding right now from. Here's a list of everybody we've been funded by. We've been funded through Naval Research Labs, which is a research group from the Navy. We have been funded by IBB, which is part of the State Department that cares about anti-censorship. Roger is shaking his head. What did I get wrong? They're not part of the State Department. They're their own group. Okay. Is that new? Or they never were? Okay. We've also been funded by EFF. We're funded by a European NGO that cares a lot about censorship resistance right now. And we're also funded by your private donations. Who else? That's basically everybody. Yeah. And no one has ever asked us to backdoor it. Well, actually, no. Actually, morons on IRC periodically ask us to backdoor it, and we tell them that would be stupid, and we kind of want people to respect us professionally, and we kind of don't want to be laughed out of the next DEF CON. So no, we will never backdoor TOR. Yeah, Lucky.
Regarding your director authority voting scheme for the implementing, did you understand it correctly that this is based on a simple majority, and then we look at the security trade-offs between a simple majority and security?
Oh, good question. So Lucky asked about directory voting schemes and why we chose a simple majority rather than some kind of supermajority, and for security trade-offs. So the general threshold is so what we do right now is you believe something if more than half of the authorities say it's so. Now, you can change when that's nice and symmetrical. Like, you believe a server is running if more than half say that it's running. You believe it's not running if half or less say that it's not running. You can set that bar in different places, and when you do that trade-off, what you get is if you set it so that every authority needs to say that it's running for you to believe that it's running, then you get a property where any single authority can keep you from using a server. Whereas if you say, and depending on where you set the bar for how many authorities you've got, this affects whether it's easier for corrupt servers for corrupt authorities to add bad servers to the directory, or whether it's easier for corrupt authorities to take good servers off the directory. And it didn't seem like either one was particularly less awful than the other, so we set it at about half. Although actually, if you have a good reason why it should be a supermajority in either case, then you should use our new proposal process. So our previous proposal process, our previous approach for modifying our specification was we would edit our specification in Subversion. Then we would edit the code to match the specification. Often we would argue about the edits that we made and put in little notes inside the specification. This created a problem where our specification did not actually specify our software. It specified our software and our intentions for our software and our disagreements about our software. Someone once said, "This reads like the Talmud." Some of you get that. So instead, we have the specification is pretty sacrosanctly what we do. We now have a proposal process where you write up a proposal, you send it to our dev list, and it gets a number, and then we all argue about it for a while. And either you build it and send us a patch, and it's got a good chance, or you convince us that it's such a good idea that we got to do it, and eventually somebody does it. So yeah, good question. Weird tangent. Next question. Yeah.
You mentioned briefly that guard selection is more complicated than the UVA.
Yeah.
And I read a while ago that there was a fingerprinting attack using guard connections. Could you talk a bit about that?
Oh yes, guard connections and fingerprinting. Right. Two questions. First, in what way is the guard selection protocol more complicated than I said? It's more complicated in a few ways. First, we don't choose randomly. We choose randomly weighted by bandwidth. We also look for the guard flag set by the authorities to say this will make a good guard. We want to choose guards only from fast, stable servers, because sometimes we want fast connections, sometimes we want stable connections, and if we always build through our guards, then we want our guards to be fast and stable. You want to drop guards not just for being down, but for being bad guards, or for being not listed in the directory, or so on. Now, fingerprinting against guards. This is an interesting topic. We're trying to figure out the right trade-offs here. If you want to come argue about it with us on our dev list, we'd really appreciate this, because it doesn't seem there's immediately an obvious answer. So it's clear guards need to be there, both to deal with the profiling attack I mentioned and to deal with some other attacks, like there was an attack on hidden services based on not having guards. Well, however, when you do have guards, you do have the problem that anybody who's doing an end-to-end connection, being the second and third hop, can figure out what, and profiling you, they don't figure out who you are, but they do eventually get a list of your guards. And this means that if you use the same guards over time, and eventually someone sees you connecting to those guards, they can link it to you. This is a problem. One solution includes using a different set of guards as you move around, but that increases your odds of eventually getting a compromised guard. Another solution is to use different guards for every IP you're at. Another solution is to change your guards over time, but if you change them over time, then eventually you'll get a compromised one. There doesn't seem to be a really trivial answer for this, but it seems like we're doing better now than we were before. Previously, to win, you had to run 2 servers. Now you have to run 2 servers for a profiling attack. Now you have to run you have to run servers and do local client eavesdropping and get lucky and hope that the client stays the same in their behavior over time, which, again, not perfect, but we think we're doing about as good as anyone knows how to make a low latency anonymity network do in this area. If you have good ideas, please get with us. We're keen to hear. And let's see, I got another few minutes. Any more questions? I can read off more of our to-do list. Let's see, I can talk about some pending proposals. I can explain stuff in more detail. Yeah.
Realizing that you're not a lawyer, from a legal standpoint, when someone chooses to put a TOR server online, is it typically
Yes, good question. I am not a lawyer. This is not legal advice. That said, the question was, given that you're not a lawyer and you can't give legal advice, do people get harassed for putting servers online? It really depends on where you are. I would not run a server in China if I were you. I would, in countries where you can be shot for owning a computer, I would not run a TOR server if I were you, because you need a computer to do it. In the US, typically, if people get with you and get with your ISP and say, hey, you're running a TOR server, or hey, some traffic came out of you that looks like it was done for something bad, we want to subpoena all of your records, give them all of your records. There are no records on your TOR server that will lead back to a client. We don't log anything interesting. However, if they decide that they're going to do an enormous sweep and try to look for evidence of some crime, like happened in Germany for a while ago, where all of the IPs that were being used to commit certain kinds of crime got hit in one massive sting on one day, dumb cops may grab your computer and look for evidence of crimes. If you are a criminal, then please stop being a criminal. If you are a criminal and you are running a TOR server on the same computer that you commit your crimes with, you are a dumb criminal. As for getting other kinds of harassment, certain services block connections from TOR because they use IPs for authentication. You may, in order to block TOR users, they may also just block the IP you're running your TOR server at. If that's also your home computer, you will not, for example, currently be able to edit Wikipedia from your home computer. You won't be able to log into certain IRC networks, and that does discourage some people from running servers. But getting a second IP isn't terribly difficult if you have, a job, or a hobby, or a university, or a lab. So yeah. All right, it looks like I'm running out of time. I hope some of you want to stay for my next talk. If not, I'm going to not go to the QA room right now because I got a next talk, but I'll be in the QA room for this track after that talk. And thank you all very much for coming.